So we're going to move up the scale here to some human population studies, and Joel Schwartz, our next talk.
Okay, so I'd like to talk to you about human studies of susceptibility, and one of the things I want to do is feed into risk assessment a little bit, and talk about the fact that if we can identify what the sources of susceptibility are, and therefore what the distribution of susceptibility is, we can provide very important additional information to decision makers. As you saw before, sometimes the distribution is narrow, sometimes it's broad. We see that in human studies too, and I think that's as important a piece of information to give to decision makers as your actual quantitative risk assessment. And so with that, let's see. All right, so you've already heard this, so I'm not going to belabor the point. There are a lot of different sources of susceptibility that we might find in human populations. But I want to make the point that when we talk about susceptibility, right, what we're thinking is, well, there's a different slope in this group or in this person than in that person, right? And so we're talking about differences in slope, and that has implications for many things, including the question you just heard raised before about NOEL levels or thresholds. So I'm going to come back to that. And so classical toxicology studies, and you've just heard how we're moving away from that, but classically they've used inbred strains with little genetic diversity. They've typically taken healthy animals, and they've typically not had any diversity with respect to age. And the human population differs from that on all of those respects, and therefore we would expect to see greater diversity in response in the human population. So that's a reason why you might want to do some human studies to look at it. And so now let me come back to this question of threshold. So if there's a threshold in the human population, in humans, for a particular substance, I would expect that threshold to vary across people due to all of those factors that we've described. So what's the implications of that? Well, suppose this is the distribution of thresholds in a population. Recall that if this is the dose at which I'm producing an event, I've exceeded the threshold. So this fraction of the population are just barely having the event induced. Then all of these people are also having the event induced because they were susceptible to even lower doses. So the dose response curve in the population is going to be the area under this curve. It's going to be a cumulative probability distribution function. Okay? So what's the implications of that? So the probability of responding is the probability that the threshold is less than the dose, and all the thresholds less than the dose produce a response. So it's going to look something like that, a typical cumulative probability distribution. But now let's come back to all the different things we've identified as potential sources of variation. We've seen evidence of many of them already. So we have age can be, and other life course events can be sources of susceptibility. Genetics can be sources of susceptibility in multiple different pathways and networks. Pre-existing disease can be sources of susceptibility, and there are multiple ones of those. Well, the central limit theorem tells us that when you start adding up distributions, no matter how skewed they are, once you start getting enough of them added together, contributing to the overall distribution, the distribution starts to look normal. And so if we have a lot of different factors contributing to susceptibility, the dose response curve is going to start to look like a cumulative normal curve in the population. And if environmental exposures are low enough that we don't expect 10% of the population or 20% of the population to suffer the event solely because of that exposure, but we think that we're down at the low end of that cumulative normal curve, the low end of a cumulative, so here's an exponential distribution of susceptibility for one susceptibility factor, and if I have 10 of them, that's what the distribution looks like. So you don't have to get that many of them for the distribution in the population to start looking normal. Forgot about that slide. And so the low end of a cumulative normal curve looks kind of linear. So as opposed to EPA's standard algorithm that for non-carcinogens, we assume there's a threshold, that may well be true in an individual, but in the population, it seems to me that that's not a very good default assumption if we think there are sources of susceptibility in the population. And so I think that's something that fundamentally has to change in quantitative risk assessments for environmental agents. Okay, now, and interestingly enough, as EPA has started to look at the data in a number of different toxins, particularly air pollutants, they're starting to see that that's true, right? They don't see any evidence of thresholds. So, for example, this is data that was created by combining 7 different birth cohort studies that had each been conducted to look at the effects of low-level lead exposure. So women were recruited during pregnancy, prenatal and postnatal blood lead levels were measured, and all of the data was combined to get more power to look at what the shape of the dose-response curve is, and it, it looks pretty linear in this range, and in fact, it starts flattening out at high doses. But certainly, there's absolutely no evidence of a threshold down to about 1 microgram per deciliter of blood lead. So for lead and cognitive effects in children, we do not see a threshold. So this bears out the argument that I just made. This is a follow-up of the Harvard 6 City study that I did, where we got another 11 years worth of mortality follow-up, and I fit 32 different dose-response curves to this data, and then I took, a weighted average using the posterior probability of the model given the data, and the weighted average of the 32 curves looks absolutely linear down to extremely low concentrations of particles in the air, basically down close to the natural background level. So in fact, when you get data on enough people to be able to look, not only does it seem theoretically that we wouldn't necessarily expect to see thresholds, we in fact often don't. This is a penalized swine looking at particles and deep vein thrombosis. This is an interesting one. This is an 11-year follow-up of a Swiss cohort study published by Sarah Downs looking at the rate of change in lung function over the 11 years of follow-up versus the particle concentration estimated at each person's address, and if they moved, it followed them around. So the mean particle concentration they were exposed to at their home address during that 11-year interval. And this is a penalized swine, which could use up to 18 degrees of freedom, but it obviously used 1. So there was no evidence of a threshold for the effects on lung function as well. Here's one where a penalized swine looking at ozone and mortality. And this one, there does seem to be some evidence of a threshold, maybe around, 15 ppb. I don't think that that's going to induce EPA to set a standard of 15 ppb, however, because, they can't even get the White House to let them set a standard of 70 ppb. So you sometimes do see evidence, but often we don't, and that shouldn't be a surprise, and it shouldn't be the default assumption. Now, there are important implications of a linear no-threshold dose-response relationship for economic analysis, because if you took Echo 101 in college, you saw this curve, you've got your marginal costs and your marginal benefits, and you know that's the right price, right? So if this is the marginal health damage and this is the marginal cost of abatement, that's where you want to set your standard. Well, but if the dose response curve is linear, then the marginal health cost of pollution is in fact a flat line. And that means you're going to be setting a standard a lot lower. Perhaps even less than 70 ppb for ozone. But if you were making an economic decision as opposed to a political one. So finding these things has very important implications for decision making, for doing risk management. So if you were doing cost-benefit analysis, this would really matter a lot. So epidemiology is very useful for looking at sources of susceptibility, and I want to give you some examples for each of the different kinds. So, for example, genetics. For example, phenotype. We see that, for example, the association between bone lead levels and heart rate variability varies with metabolic syndrome. With obesity and diabetes. Diabetes also modifies the effect of lead on renal function. So those are examples that have been seen. Air pollution has been associated with a lot of things that diabetes is associated with, so it seemed plausible to look at diabetes as a modifier of air pollution effects as well, and in fact people have seen it. So Goldberg looked at air pollution and mortality in Montreal and found that diabetics were more susceptible. We looked at hospital admissions and found they were more susceptible, and there have been many studies since then that have identified that. And it's also true, and these studies use like millions of deaths in many cases, right? So that's how you get the power to do these kinds of things. So there are physiologic studies suggesting that diabetics respond to particles, for example, differently than non-diabetics, looking at a range of other physiological factors such as QT interval, ST segment depression, etc. So we also see that diabetics respond differently than non-diabetics in looking at inflammatory markers in the blood. And that obesity modifies the effect of air pollution on inflammatory markers in the blood. And so there's a lot of data suggesting that diabetes is an important risk modifier for the effects of air pollution as well as the effects of lead. Now, if diabetics are more susceptible because they already have these pro-inflammatory and oxidative stress processes elevated in their body, then maybe we ought to take a look at that as well. And so there have been a number of candidate gene studies which legitimately do have a bad reputation, right? But candidate gene studies looking at genetic polymorphisms in oxidative stress genes and air pollution. And what I will say is that in contrast to looking at the main effects of genes, there has been some replication in this case. And so I already said that. And I think the strongest message comes in looking at respiratory responses, because several different groups, the group in Southern California with children's study, Isabel Ramure in Mexico, we looked in the normative aging study in Boston. There have been quasi-replications all suggesting that polymorphisms in genes related to oxidative defenses seem to modify the respiratory response to air pollution. So I think there's enough of that we can conclude there's probably something going on here because of the replication. And here's one example. This is looking at NO2 associations with asthma prevalence based on a polymorphism in NQO1. But GSTs tend to actually be the things that show up most often. So we also created a score. Ours was not sophisticated. It wasn't weighted. We just took the number of unfavorable polymorphisms that we had genotyped in our population, and we split on the median into low and high oxidative stress scores, and we looked at the multiple moving averages, like the previous 4 hours, the previous 24 hours, the previous 3 days, etc. And this is looking at the percent change in fibrinogen in the blood for an interquartile increase in black carbon, diesel particles, basically. And what you see is starting right away at 4 hours, but with the effects slightly larger. If you look at a longer averaging time, you're definitely seeing increases in fibrinogen levels in the blood in the people with the high oxidative stress scores, that is to say, lower defenses against oxidative stress, and really there's nothing significant going on in the people with the favorable polymorphisms. So that's looking now, moving from respiratory to some other kinds of outcomes. Cardiovascular. This is looking at heart rate variability in people with the good genotypes, in people with the high variable number tandem repeat for heme oxygenase with the deletion of GST-M1 and both. And again, we're seeing some stuff going on here. What we don't have here is a lot of replication in other data. So we need to take this as maybe it's worth somebody else doing this to see if they can repeat it, and until that happens, we don't know. But it may be that it's not just respiratory responses where oxidative stress polymorphisms matter. And here's another example looking at that decline in lung function in the Susceptibility study by genotypes, and again, you can see that heme oxygenase and GST-P1 are showing up there. Epigenetics may also matter. This is the percent change in fibrinogen with particle number concentration in the air by methylation category of factor 3, and which is also in the chain of thrombus formation, right? And so what we see is that when there's low methylation for factor 3, we see a bigger signal with air pollution increasing fibrinogen. So DNA methylation, epigenetics may also modify the responses, which is starting to suggest that there are a lot of things modifying responses, and the central limit theorem argument is a pretty good one. But social factors also matter. So this is looking at the effect of wintertime temperature in the Worcester heart attack study. This is a population registry of heart attacks in Worcester County. And we matched them to controls, and we looked at what was the effect of decreasing temperature in the winter on the incidence of myocardial infarction. And what you see is a clear dose-response relationship with income. So, my guess is that everybody in the room doesn't have to worry about having a heart attack when they get cold. But there are other people out there who do have to worry about having a heart attack when they get cold. If you live near a little lake or a pond, that obviously modulates the local temperature relative to what the weather station says. And again, you're protected. So that does suggest that adaptation by urban planning might be protective against this. So we see, here's another study. This was looking at, by Marie O'Neill, looking at 4 cities, looking at the effect of heat. What's the excess mortality at 30 degrees compared to 15? And, the answer was about 6% more people died on those very hot days. But look at the difference by race. And look at the difference by education. We clearly have, social factors are clearly central in the effects of climate, in the effects of weather on mortality. And so we need to deal with that. This is looking at effects of air pollution in different cities, depending on population density, depending on how variable summertime or wintertime temperature was, and depending on how much of the particles came from traffic. Traffic particles were worse, and very variable summertime temperatures seem to increase susceptibility to air pollution. So that's an interesting observation. In lead, we find that being raised in enriched environments mitigates the effect of lead on exposure in animals, and we're seeing, similar things in children, in humans, when we look at socioeconomic status, for example. Stress. Most of the lead you take into your body, you can't get rid of. We don't really have a good way of getting rid of lead. It gets socked away in your bones because it's a divalent cation and your body thinks it's calcium. But it comes out of your bones also. The bones are dynamic, and also you lose calcium as you get older, right? Psychosocial stress on primates leads to more mobilization of lead out of the bones, so you get exposed to the lead that you were exposed to as children again when you get older, and it happens more if you're under more stress. So tell your boss to back off a little, But another key thing for risk assessment and for giving information to decision makers is to look at the geographic distribution of risk. So I already told you that we've found socioeconomic factors that modify the risk of heat. Age modifies the risk of heat. We've also seen that diabetes modifies the risk of heat. So if you take all those things together, you can try to create a sort of weighted cumulative score of how much susceptibility there is in every census tract in New York City. And so we published this in EHP a few years ago. And what you see is that there are places where there's much higher vulnerability than other places in the New York metropolitan area. Well, that's important to know because now, you can figure out where you want to target measures to intervene. If you think there's a heat wave, where you need to particularly send those sound trucks to tell people that they can go right to the armory and it's air conditioned. If you have a plan to plant 1 million trees in New York, you now have an idea of which neighborhoods you want to start in, right? So this kind of information, which you can only get by looking at the distribution of susceptibility, can be very important in terms of improving public health. I want to end by showing you a make-believe story, okay? And my make-believe story is what having multiple factors that produce susceptibility might do to the risk of an important consequence. Not that I know this is true, but that it's plausible that things like this might happen. And so here's how it goes. It turns out that Michael Marmot has shown that the risk of myocardial infarctions varies substantially by tertile of income using a representative U.S. sample. There's also a number of studies, one of which used the entire Danish population. Only in Scandinavia can you get away with this. HIPAA clearly doesn't exist there. But they can look. They don't have any selection bias, right? They have the whole population, and they looked at what the risk was of diabetes for having a myocardial infarction. And then from the Nurses' Health Study, I took the published risk of having a myocardial infarction from exposure to particulate air pollution. So far, that's all real data. So now I assume that diabetes might double the risk. This is for long-term exposure to particles, so there's no data on this. But suppose it doubled the risk of having a heart attack from particles. And suppose some genetic profile doubled the risk of having heart attacks from particles. And suppose particle exposure was a little higher in the low-income tertile than the high-income tertile. Okay? And then you take what the baseline rate of heart attacks is in the United States, which is not small for a lifetime risk, right? And you ask, what would I find the incremental risk, absolute risk, would be? So this is the distribution of the incremental absolute risk, as we heard someone talk about earlier today. And, most of it is kind of small. It's, a 1 or 2% increase in absolute risk. Now, that's 10 to the minus 2, right? Which, if we were talking about lifetime risk of cancer, we regulate way smaller risks than that. So a 10 to the minus 2 lifetime risk of having a heart attack because of particulate air pollution exposure is not a trivial thing. But, look at that. There's actually a small but not infinitesimally small population that's getting like a 70% risk of having a heart attack because they're low-income diabetics with the wrong genetic profile. Solely, right, a 70% risk due to particles in the air. Now, if this were true, and I made it up, right? But if this were true, I would think that the administrator of EPA would want to see this figure in deciding how we're going to control particles in the air. So it seems to me that capturing what the actual sources are of variability as opposed to putting in, an adjustment factor for the fact that there's a range, looking at how they're distributed in the population, looking at what subgroups that are identifiable are, looking at geography is going to be increasingly important in doing risk assessment for environmental exposures. And so here is, let me close with this. This is from a paper by John Levy where he looked at different alternative ways of reducing exposure to particles by controls on coal-burning power plants. So alternative ways to require controls, where the controls are, how much, etc. And he plots that on a graph that has two axes. And one is the health benefits. So obviously stricter controls save more lives per year. But the other is the amount of inequality in the distribution of the risk imposed on the population by their exposure to particulate air pollution. And there's quite a range of variation in the amount of equity benefits, so that here are two alternative strategies that save the same number of lives, but this one reduces inequality by a lot more than that one. And I think again, this is the kind of information that we want to provide to decision makers so that they can make thoughtful decisions. And to do that, we need to identify the sources of variability, identify what these differences in the distribution of risk are. So, thank you.
We'll take a couple of questions. I think we have 3 right now.
Joel, thanks very much for a very enlightening presentation. I just want to remind people that the Clean Air Act, and you know this, requires that we protect the most sensitive persons or groups. And so, in fact, your giveaway at the end, which was EPA administrator, wake up and take a look at this, because the subgroups, especially if you can begin to think about their distributions beyond a Gaussian curve, are extremely important and have enormous implications for where those standards ought to be set. It's not a question I'm sure you would agree, but I just wanted to congratulate you on making this crystal clear.
Thank you. I think the problem isn't the administrator. I think the problem is Cass Sunstein.
So,
or the president.
So I think before we go too far with this, I think, one of the things we may want to get into in our discussion is what are the implications for informing decisions? And really what we're thinking about are there different ways to begin to protect populations when we have these kinds of distributions within a population? So there's a good example of that comes from the original ozone standards, which was the administrator's decision that we're not going to protect the jogging asthmatic.
Right.
But we are going to tell people when there's bad air days, and we are going to make sure that physicians know that they need to give asthmatics emergency medications to be able to deal with some of those things, even though we may not set our standards like that. So I think there are some opportunities for us to talk about that when we get into the discussion today. We've got a couple more over here.
Risha Putzrath, Navy and Marine Corps Public Health Center, though the comments I'm about to make are my own. We need these disclaimers, otherwise I can't come. I have actually 2 questions regarding your initial theoretical analyses that you presented. It was only up for a short time, but I think the curve you had where you showed that there was a linear dose-response curve, if I'm not mistaken, given the numbers on the x-axis, that would be a log dose response curve. And it would be my understanding that if it were linear in log dose, it would not be linear in dose. Is this correct?
Well, so 2 things. The curve I showed was, I just generated a cumulative normal distribution and took a slice off. So the numbers on the x-axis are meaningless. I just wanted to show what the bottom...
But was it in normal space or log dose space?
It was in normal space.
Okay.
Okay. Would there be a difference if it's linear on the log scale? Well, that's an important question because most of the epi models that I showed you were in fact relative risk models and not additive models. So they are, log linear, right? So in principle, a linear dose response curve there is exponential, right? In untransformed space, but the slopes, aren't, fortunately the slope for particles isn't huge and we're not all dead, and so, if I have something that is a major public health problem, it accounts for 2% of the deaths in the United States, right? Which, with 2.4 million deaths, right, that would be like 50,000 deaths a year or something. That would be a big deal, right? If the relative risk is 1.02, then if you take a Taylor series expansion, it's basically going to look linear also. So it only starts to get nonlinear when you start to get to higher risks. And that may happen for some environmental agents and some health outcomes, but for others it clearly won't.
Oh, the second question I had on your theoretical development was the use of the central limit theorem. And I was wondering what data you had to support the concept that those distributions should be additive, especially given that a lot of them will be on different metrics, everything from milligrams per kilogram per day to area under the curve to degrees of temperature to dollars earned.
Well, I mean, I don't think the metric really matters, right? Because I can, standardize those things, right?
So
I mean, the question is, I have a distribution of susceptibility due to income. I have a distribution of susceptibility due to, hemoglobin A1C levels.
If I may, I'm not asking whether the data should be combined, but for the central limit theorem to hold, they have to be added. And there are other methods of combining than adding. So I was wondering if you have any data to support adding as the metric for
okay.
the method
So
for
I think
combining.
that's separate from what the scale of the variable is.
I disagree, but go ahead.
You can turn it all into z-scores. It's possible that the results might be multiplicative as well. I mean, if I have susceptibility to two different things between some kind of disease status, like hemoglobin A1C level, due to age and due to genetics, to a first approximation, I might think that those things are distributed independently. But biologically, they might interact, so indeed, you may want to multiply those things. So it's possible that we have multiplicative effects. If you look at the literature so far, there's not a lot of data to suggest that two different sources of susceptibility are producing multiplicative interactions, but we may turn out to find that. I don't think it would change the argument very much.
Cheryl Walker, Institute of Biosciences and Technology. First, I just want to thank you for a great talk that was understandable even by the non-epidemiologists. That was really great. The question I wanted to ask was some early work that I certainly was familiar with from a review from Barker. I'm not sure if he actually did it, which actually pointed to an underlying cause for some of the socioeconomic risk, which had to do with early life exposures. And I know this is a theme that this committee has dealt with before, where, for instance, very small birth weight and an inadequate in utero environment could predispose an individual to be less well able to handle stress. And in fact, those individuals would tend to segregate into different socioeconomic groups. And in fact, that could actually underlie some of that correlation. And so my questions would be, first, A, is that actually true? And then the second question is, if so, what do you think that is contributing to what you were showing us today?
Well, so certainly we see that prenatal events, including prenatal exposure, have impacts on children. There's some evidence on prenatal lead exposure and things like that. There's some evidence that epigenetic changes that occur prenatally influence later life course and stuff like that. So in terms of, is there some evidence to support the Barker hypothesis? I think certainly not only is there epidemiologic evidence, but we're starting to see things like epigenetic mechanisms that might explain why that could happen. Interestingly, there was a paper published a couple of years ago showing that DNA methylation in umbilical cord blood was associated with lead in the umbilical cord blood. So environmental exposures may be having those effects. And of course, there's Randy Jerdel's stuff on bisphenol A. So that may be part of the mechanism. I think it's going to be hard to tease that out epidemiologically because of a disturbing feature of our society, which is that socioeconomic status has become predominantly hereditary in this country. The probability of transitioning from the lowest quartile of the SES ladder to the upper quartile of the SES ladder, if you're not an immigrant, is extremely small. We still see moving up the SES ladder in immigrant groups, but not for native-born Americans. We have a lot of social stratification. So at that point, it becomes very hard to tell the difference between what your SES was when you were a young child or in utero and what your SES is when you're 30, because they're the same. And so it's going to have to be, I think, more mechanistic studies that will allow us to tease that out.
Thank you.
Thanks. Marilee has a couple of comments about our lunch break, and we're going to break for about 45 minutes. So, Marilee?
Okay, so we'll come back at about at 1:30, Bill?
1:25.
1:25. So that's a little bit longer than what's a little bit later than what's listed on your agenda. There's food available on the third floor. There's a cafeteria for the speakers, committee members, people with a dot on your name tag. We do have a lunch provided in room 105, which is on the opposite side of this wall. And if the cafeteria upstairs gets full, we do have a McDonald's that way and a Burger King that way. But I can't say what that's going to do to your health.